finding the starting points of planets is something other than investigating space. It's a journey that could address the greatest, inestimable secret of all: the way that we became the building blocks of planetary systems. The planets in their initial gassy stages are disguised inside protoplanetary disks. We can only imagine how grandiose areas like our own have changed over time unless we fully perceive these basic processes. Today, our understanding has grown larger than ever before. We must make sense of what has happened by understanding the shared traits that could support life. This is a fundamental objective of this study, which goes beyond the realm of academia. Learning about planets in their early stages brings us one step closer to understanding what it takes to make a livable planet, beyond just being a celestial body. In this undertaking, we might not only find new planets but also perhaps signs of something happening beneath the surface of the universe beyond our little blue dot. Investigating a planet in its infancy is like attempting to unravel its genetic code. This journey dives deep into the vast cosmic soup to find how complex systems form, going beyond basic galactic body indexing. Understanding the intricacies of planet formation, hidden in the whirlwind of protoplanetary disks, is key to our understanding of not just the origins of planets but also their development to support complex and significant phenomena like life. This research has broad implications that extend beyond academia. By doing so, we shed light on the existential question of whether or not life might arise anywhere in the universe. Planet formation provides a starting point for unraveling the complex web of conditions required for life. Finding extraterrestrial life is only part of the story. A more complete view of Earth's place in the universe relies upon our ability to determine the specific conditions under which life could thrive. In our quest to find extraterrestrial life, we are entirely lost without these insights. There are many different types of conditions where life could arise, and we run the risk of missing the details that make some worlds viable. With each new discovery in planetary formation, we draw closer to solving perhaps humankind's deepest question: how far are we from the stars? The James Webb Space Telescope is set to shed light on the baffling protoplanetary disks and other deep space objects with its unrivaled infrared vision in its quest for cosmic knowledge. This next-generation observatory is not working alone, but rather at the center of a vast cooperative network, drawing on the achievements of its predecessors and contemporary partners, such as the Hubble Space Telescope and the Atacama Large Millimeter/Submillimeter Array, ALMA. In addition to ALMA's data on millimeter and submillimeter frequencies, and Hubble's optical and ultraviolet vision, Webb's special suite of instruments can peer into the infrared range with unparalleled clarity and sensitivity. When it comes to studying how planets are formed, this trio of observational powerhouses works in tandem to provide a more complete picture of the universe. Webb will add to the body of knowledge left by Hubble and ALMA by working alongside them to further understand their observations. Webb will examine the thermal emissions from protoplanetary disks, building on Hubble and ALMA's past work uncovering their complex features, such as gaps and spirals that might contain forming planets. The ability to detect the thermal radiation emitted by baby planets and dust grains will provide astronomers with important data on the composition of these celestial nurseries and the processes that shape them. Moreover, the cosmic dust that frequently obstructs our view of these young planetary systems makes Webb's infrared spectral capabilities ideal for piercing through this dust. This ability will reveal aspects of protoplanetary disks that were hidden from previous observatories, such as the disk's interactions with its central star and the initial stages of planet formation. Astronomers will gain a better understanding of the disk's dynamics and will be able to confirm the existence of planets, illuminating the development process. By combining Webb's views with data from Hubble and ALMA, studying the chemistry of material accumulation and the interactions between the disk and stars are all essential parts of this for a detailed picture of the planetary system's evolution, from the formation of fully fledged planets to the breakdown of interstellar clouds. Such comprehensive insights are vital. Together, Webb, Hubble, and ALMA show how powerful it is to utilize multiple observational stages, each with its own strengths, to understand how planets are born. In the ongoing search for knowledge, this collaborative effort will surely elevate our understanding of the universe, providing answers to ancient questions while also raising new mysteries. Through its deep space observations of the protoplanetary disks HL Tau, SAO 26462, and MWC 758, the James Webb Space Telescope has uncovered a complex and fascinating web of information that challenges our current understanding of how planets are formed. The distinct features revealed in each of these disks, a whirlwind of gas and dust orbiting baby stars, offer clues about the intricate and ever-changing processes of planet formation and evolution. The intricate patterns within the disk of HL Tau, a young star about 450 light-years from Earth, have been beautifully revealed by Webb's observations. This system was studied with Webb's infrared telescope because it is known for its remarkably clear gaps and rings that resemble the early stages of our own solar system. To better understand the material distribution and potential signs of planet formation, the observations aimed to penetrate the thick haze of gas and dust surrounding it. In spite of all the anticipation, the surrounding material offered both advantages and limitations. It allowed us to see the building blocks of planets but obstructed our view of the body as they were forming. As a result, attention shifted to SAO 206462, a protostar with a disk notable for its exceptional spiral arms. Webb set out to investigate what causes these fascinating patterns. Previous research had pointed to a massive planet carving a path through the disk, but Webb's findings contradicted that theory. Instead, the telescope detected signals from a planet that might be in the process of forming, rather than the gas giant that had been expected. Not only does this discovery show that planet formation can take unexpected turns, but it also highlights how difficult it is to predict how these complex dynamical interactions will unfold. In another case, Webb observed the disk of MWC 758, another protoplanetary system with spiral arms, to determine the characteristics of the potential planetary makers responsible for these features. Despite hopes of discovering a planet in the process of development within its spiral structure, Webb's observations were even more revealing than anticipated. Effectively extended, the riddle of the complex nature of concentrating on these distant universes is featured by the way that planets in this framework have not been straightforwardly distinguished during their development. This shows that the objects impacting these circles may be more tricky, smaller, or clouded by dust than initially thought. Along with before data from ALMA and Hubble, these Webb discoveries are changing our thought process about protoplanetary disks and the youthful planets they contain. The discovery of conceivable new planets and the shortfall of expected ones both highlight the intricacy of planet creation, which led to these astonishing outcomes. They show us a universe where the course of creation is nowhere near direct, but rather a winding road loaded with secrets, prepared to be disclosed by the hounded observation of our generally powerful telescopes. Tracking down planets when they are still in their beginning stages is as troublesome as attempting to make out the glimmer of a light under a brilliant spotlight. The monstrous vacancy of space, also, and the thick, dusty airs wherein these youthful planets are conceived, just make matters worse. Stargazers should utilize frontline innovation and novel ways to deal with catch a brief look at developing planets, since these heavenly bodies are so faint compared to their host stars. The issue of contrast is one of the major deterrents. It is incredibly difficult to straightforwardly recognize planets in line since they are ordinarily a great many times fainter than the host stars. To get around this, space experts utilize techniques like coronagraphy, which involves coordinating the radiance of the star away from the planets so they can be seen, notwithstanding their actual lower iridescences. Yet, even with present-day innovation, the light from the material around the star can veil the smallest indications of planets in line. To make up for the barometric obscuring that ground-based telescopes experience, versatile optics gadgets are fundamental. Webb and other space-based observatories are vital in light of the fact that these frameworks have limits, particularly in the infrared range, which is where protoplanetary plates and creating planets produce most of their light. Another test is the intrinsic shakiness and alterability of protoplanetary plates. The presence of planets in their beginning phases can be clouded by the gas, residue, and trash that fills these circles, which gives a confounded background. Cosmologists use the infrared abilities of telescopes, for example, Webb, to look through these covers and identify the hotter parts held inside the plate. Besides, spectroscopy, and other comparative techniques empower researchers to recognize synthetic highlights of disk parts, which might give light on the fundamental growth and arrangement mechanism. The usage of backhanded proof to find the presence of planets in line is another book approach. Plate structures like holes, rings, and twisting arms can be ascribed to planetary gravitational pull and are concentrated by stargazers. Researchers can track down designs that fit with thoughts of planet development by considering the development and circulation of gas and dust in these plates. The distinguishing proof of planets in line is as yet a troublesome puzzle, even with these state-of-the-art techniques. Understanding the complex connection between residue, light, and gravity in the turbulent star nurseries calls for inventive and multidisciplinary strategies. Moreover, to high-accuracy sensors, the inquiry to appreciate the beginning of planetary frameworks is extending human comprehension and revealing the perplexing dance of creation. As innovation and strategy form bits of knowledge into the cycles of planet development and the early circulation of materials in creating planetary groups, revelations made by the James Webb Space Telescope and its joint examinations with different telescopes not only extend our understanding but also force us to re-examine our current comprehension of planetary development and the models and speculations that endeavor to represent it. Discoveries of previously unseen planets and complex designs within protoplanetary circles are instances of the startling perceptions that give us observational proof. These observations both test and work on our hypothetical models for planetary disk features. Highlights like winding arms, holes, and rings may now be all the more dependably related with the gravitational force of planets. Data giving an unmistakable, discernible connection between circle qualities and planetary development instruments. By integrating these new results into their reenactments and speculations, space experts can move along models of planet development, including the core growth model and the disk shakiness model. The exact estimations of the residue, gas, and perhaps ice appropriations inside these circles give insight into the early conditions that led to planets. We can look into the makings of the planets and whether they are tenable, thanks to Webb's planning of the circle's warm emanations and compound marks. The obtaining of climates, oceans, and possibly life-supporting components via planets can be better understood by diving into the circulation and dynamics of these materials. Webb and comparable missions have shed light on the developmental ways taken by planetary frameworks through the data they have gathered from the first residue and gas cloud breakdown through the birth of a completely evolved planetary group. Cosmologists can assemble a more complete timetable of planetary advancement by concentrating on frameworks at various stages of arrangement. These discoveries give light on the instruments of protoplanetary circle breaking down, planet relocation designs in these frameworks, and stable planetary circle development. Interest in gas giants' roles in controlling planetary frameworks conditions is high, particularly as it connects with the chance of livable planets like Earth. The soundness and livability of inward planets are kept up with, as per theory, by gas giants like Jupiter, safeguarding them from the constant invasion of comets and asteroids. Arrangement, movement, courses, and impacts on planetary framework engineering might be gathered from Webb's perceptions. Our knowledge of how tenable zone worlds, like Earth, could maintain tenable conditions could be enhanced. Thus, these discoveries have sweeping ramifications for astrobiology, the study of extraterrestrial life, that relies upon our insight into how planets formed and developed. We can thank Webb for expanding the scope of livable zones and improving the probability of finding life-supporting planets by determining the conditions under which planets form and the variety of conditions that can support planetary systems. Generally, our knowledge of the universe has progressed incredibly because of the discoveries made by Webb, and the combined consequences of our joint perceptions are also enhancing how we might understand the formation of planets and planetary systems. They expand our perspective of the conditions that could support life, driving us to uncover new areas to explore in our quest for vast understanding. An astonishing new chapter in how we understand how planets start and evolve has begun with the discoveries of remarkable planetary candidates and complex disk structures, made possible by the James Webb Space Telescope. As we look forward, there are so many possibilities for new discoveries that could significantly impact the way we see the universe. The initial Webb observations have set the stage for an in-depth study of the properties of the planetary candidates that have been found to better describe these possibilities. Future observations will utilize Webb's unparalleled sensitivity and resolution to conduct follow-up research. Space experts expect to discover the majority of compositions and air characteristics of these infant worlds by analyzing their light broad descriptions. These studies will demonstrate that these objects are indeed planets and shed light on the many different ways planets come to be, revealing their compositions and structures. Our understanding of how planets form will be significantly improved by Webb. Direct imaging of circumstellar disks and the discovery of protoplanetary cores are among its highlights that enable the study of the earliest stages of planet formation within protoplanetary disks. Theoretical models of planet formation, such as core accretion and disk instability theories, depend heavily on these data. With Webb's help, we can better grasp the complexities of planet formation by tracking the dynamics of gradual accretion processes and mapping the distribution of dust, gas, and ice in these disks. This data can either strengthen or disprove current theories. The larger goal of understanding the origin and evolution of planetary systems depends heavily on Webb's observations, which extend far beyond the immediate goal of identifying specific planet candidates. A more complete history of planetary system evolution can be built with the help of Webb's investigations of systems at various ages, from the first protoplanetary disks to older systems, planetary migration, and its effects on system architecture, the potential of stellar feedback in determining planetary zones, and the establishment of stable, habitable conditions. These are aspects that must be understood. Interdisciplinary collaboration and technological advances are essential for the future of planetary formation investigations with Webb. A more complete picture of planetary systems will emerge from the combination of Webb data with that from space missions, ground-based observatories, and theoretical models. Webb, along with other observatories, will continue to push the boundaries of discovery as new instruments and technology allow us to detect fainter objects, resolve finer details, and access a broader range of frequencies. The broader impacts of studying planetary system evolution and answering more general questions about the plausibility of life beyond Earth will be greatly enhanced by Webb's continuing and future observations. As a giant leap forward in our quest for cosmic understanding, Webb's discoveries will guide our search for habitable planets and extraterrestrial life by illuminating the conditions under which planets form and evolve. In conclusion, Webb has immense and empowering future potential in the field of planetary formation and system evolution. We are becoming increasingly more connected to the universe and our understanding of it as we gain a better grasp of the complex mechanisms that govern the formation and evolution of planets and planetary systems. With each observation, our exploration of the universe is just getting started. As the James Webb Space Telescope brings us one step closer to groundbreaking findings, new information will continue to emerge. Our understanding of the intricate, creative flow that shapes universes and forms planets is evolving, one observation at a time. Thanks to Webb, we are beginning to grasp the vast mysteries of planetary creation and the evolution of celestial bodies. The spotlight is now on you, the audience. How do you feel about these groundbreaking discoveries? Considering these new facts, how do you think our perspective on the universe and our role in it will change? Leave a comment with your questions, feelings, and thoughts. Please like and subscribe to our channel if you share our wonder at the grandeur of space. By contributing, you enable us to uncover more secrets of the universe, allowing all people to share in our awe at its magnificence and complexity. Let's continue this celestial journey through the sky. If you remain curious, keep exploring.